Okay, folks, we should be in class. We're not in class. That annoys me. Watch the final video for Chapter 14. Bring any questions you have about Chapter 14 to class on Monday. Plan to turn in Test 1 on Monday. If you have any questions about said test, let me know. Send me an email. You don't really have an excuse here. Remember, you don't need to print out the test. Not necessarily. You're essentially answering those test questions on a separate sheet of paper. So, this last part is a little tricky. The idea here is that the mechanism is dependent on the slow step. If one particular step is slow, it slows down the whole process. And if step 1 is slow, it doesn't matter how much concentration of step 2 you have, it brings things to a grinding halt. If you're grocery shopping and you have like a dozen baggers, if you only have one cashier checker, doesn't matter how many baggers you have. Everything's going to slow down between that one cashier. But on the other hand, even if you have a lot of cashiers but you have no baggers, it's going to slow everything down. On the other hand, because the cashiers have to then slow down to help bag. So things can speed up or slow down depending on which guy is limiting. So sometimes, though, concentration will matter. That on certain conditions, even if step 2 is slow, step 1, if step 1's concentration is low enough and step 2's concentration is high enough, the rate can invert. The example I want to give you real quick is if you're watching the video, I talk about ozone decomposing and monooxygen decomposing is this 2-step reaction using NO and NO2. Well, it's true that the first step has a slower rate constant. However, in the lower troposphere, where ozone is most concentrated, the first step is actually faster because the concentration of monooxygen is so low. And so the rate is actually dependent on monooxygen concentration and not ozone. But in the upper troposphere, where there is more high-intensity light that can split oxygen into monooxygen, the second step becomes significantly faster, and the second step is not the slow step, and so the first step becomes the slow step. So it all depends on concentration. Things can slow things down, but that changes your rate law. The rate law we see does not always match the chemical equation because there's many complicated steps in there, and that's one of the ideas. You need to be able to propose possible steps that make sense that would give us a rate. This is why this field of science is so well studied, because like polymerization, people make polymers out of hydrocarbons and they want them to have certain chain lengths that give it certain properties and stiffness and such like, and they can know if I add this much of reactant A to this much reactant B, I'm going to get this chain length of polymer based on many different competing factors. And they can predict how much polymer they're going to get and what chain length based on different starting conditions. So it's very useful field in materials engineering. But watch that video, watch that video, watch that video. If you have any other questions, we'll try to get to them on Monday. But in the meantime, watch that video, work on that test. We will plan on doing the lab, the proper lab, the freezing point depression lab this week starting Monday. Okay. Have a good day.